Example 7.4 is going to show us how to approximate a definite integral using trapezoids. So this is going to be a much better approximation than just Riemann sums. If we review real quickly, if I have a function that I'm approximating with a Riemann sum, I just approximate it with a constant, with just a rectangle. So that's not really that good of an approximation because we have all of this error. But if I have that same function and I approximate it with a trapezoid, that's me approximating the function with a straight line, not a constant. So you can see we are going to cut down our error quite drastically. And let's review how to find areas of trapezoids. If I have one trapezoid that looks like this, and another trapezoid that looks like this, and let's say they both have the same base, b. And let's call this height 1, this height 2, and this height 3. So the area of the first trapezoid will be base divided by 2 times h1 plus h2. It's really the same thing as area is equal to base times height, but here you have two heights that you have to average first. So h1 plus h2 divided by 2. This trapezoid has an area equal to base divided by 2, h2 plus h3. So both of them have a common base, so we can pull that out, and as well as the division by 2. And we're left with this h1 right there, and h2, but then we also have this h2, so we've got two of those, right? This height right there is shared between those two trapezoids, so it gets counted twice. And h3 only occurs once. So any interior height in your trapezoid approximation has a sum of 2. Now, with all this in mind, let's go through this rule. Here we wish to approximate the area underneath x squared over the interval 1 to 2. So let's give ourselves a sketch of what's going on. There's the x squared function, and this is the interval 1 to 2. If I want to use 4 trapezoids, then the base of each trapezoid will be b minus a over n, so 2 minus 1 over 4, or 1/4. So my first trapezoid will go from 1 to 5/4, and then to 6/4, and then to 7/4, and then finally 8/4 is the 2. So if I can give myself a rough sketch of what this is going to look like. There's our first trapezoid, our second, our third, and finally our fourth. So it gives us a much better approximation than just the Riemann sum. So this integral between 1 and 2 of x squared is approximated by the sum of these areas of trapezoids. They all have the same base of 1/4, which we divide by 2. And now the first height occurs once, so we'll take f at 1. But then this height occurs twice because it's shared between those two trapezoids. So we have 2 f of 5/4. Our third height is also shared between trapezoids. It's an interior height. So we have 2 of the f of 6/4. We also have 2 of the f of 7/4 because that height is shared. And then when we get to our last height, that is only involved in the area of the last trapezoid, so it's only counted once. So your first height and your last height are only counted once, but all the other heights in between are shared between the trapezoids, so they get counted twice. Okay, so we have a 1/4 being divided by 2. That leaves us with a leading 1/8. And if we plug 1 into our function, we get a 1. If we plug a 5/4 into our function, x squared, we end up with a 25 over 16. But if we multiply by 2, we end up at 50 over 16. So let's underline them as we go. Now we have 2f of 6/4. So after you run through that algebra, you end up at 18/4. And here we have 2f of 7/4. That's 98/16. And then we have f of 2, which would be a 4. So when the algebra clears the room, we end up at 300/128, or about 2.3438. So this function, we actually didn't even need to use an approximation, right? We can actually find an antiderivative of x squared and use it to find the area. So let's find the exact area, right? This was an approximation with trapezoids. To find it exactly, we take an antiderivative, which would be 1/3 x cubed, and evaluate that antiderivative at the bounds 1 and 2 to find the difference. So this will be a 8/3 minus a 1/3, or a 7/3. And 7/3 is about, actually, hold on. We can just find the difference. Let's find the error in the approximation. So the exact value, 7/3, minus our approximate value, 2.3438, wrapped in absolute value, leaves us with an error of 0.01042. So it's a pretty decent approximation.